Hello one all, this is Jasneet Singh, a.k.a. Innovative Coder from Innovative Coder Workstation, and in this video I'm going to talk about, in last session we discussed about linear regression as a classifier. In this session we are going to talk about an algorithm called logistic regression. We have a brief idea about that algorithm, and now in this video we'll be continuing with it, and we'll be deep diving into the stuff. Although it is named as regression, the logistic regression algorithm, but it is a classification algorithm, so it is used as a classification algorithm. All in all, there were actually two main problems as we discussed in the video in the previous. Okay, so let's go to the hands-on session. Okay, so the first problem which we discussed in the previous session was that on adding a few extreme values or outliers, the complete model changes. That is, our decision boundary shifts completely. It shifts drastically, really drastically, and that should not happen, as we saw in the graph, right? So just let me draw the graph. As we saw in the graph, we had, okay, my pen is not working. Fine. So we had this kind of a graph where we had these values over here and these values over here. We had our decision boundary like this, and upon adding some extreme values, our decision boundary shifted to this, right? And this should not at all happen, right? So that was a problem which we dealt with. Another problem was less than 0 and greater than 1. So what is this less than 0 and greater than problem? One problem, just recapping and revising it, which means that if a model predicts a value as large as 100 or maybe 1000, then the approximation functions wraps it up to 1, and same is for values less than 0, right? So we had our approximation function, which was kind of just having the 0.5 value as a cutoff value, and everything less than that 0.5 was wrapped up to 0, and everything greater than 1 was wrapped up to 1, right? So that was a problem which we were having, and this should not happen, because when you have kind of a 1000 value and it wraps up to 1, then there is kind of a serious problem. So to deal with these two issues, we come up with a function known as sigmoid function, and sigmoid function we'll be looking a lot in this complete machine learning as well as deep learning series, because sigmoid function is what the basis of these deep learning algorithms, these neural networks. Moving forward in sections in coming sessions, you would be seeing sigmoid function a lot. So talking about what is actually sigmoid function. So sigmoid function can be written as s of z. We represent the sigmoid function as s of z 1 upon 1 plus e to the power minus z, right? So if we if we plot this graph of sigmoid function, it would look like this. And please, I have a really bad handwriting, drawing, even handwriting, so please bear with me. This is the 0, and here we have 1, so this would be a little bit like kind of cut off at 0.5, and this. So this is kind of an asymptote we have over here at 1, right? 0 is an asymptote and 1 is an asymptote. What does asymptote means? Asymptote means that it will try to reach towards one value but would never touch the 1, right? So till infinity it would try to reach 1 but it would never touch 1, and same goes for 0 as well. Towards negative infinity it would try to touch 0 but would never be able to touch 0. Okay, so let's see what values we get if we just see it in terms of limits. Okay, so now we see the limits. So when z tends towards negative infinity, our complete this e to the power minus z would tend towards infinity, right? E to the power negative of negative infinity is positive infinity, e to the power positive infinity is infinity, right? And when this complete, s to the power z equal s of z, which is sigmoid function of z, equals to 1 upon infinity, then s of z would tend towards 0, right? And in second case, as z tend towards infinity, then what do we have is e to the power minus z would tend towards 0, right? And this goes 0. So what do we have? S of z tend towards 1. And this is what this graph shows. Fine. And for as I marked the point as well, you might have guessed, for z equals to 0, this would be 1 by 2, which is 0.5. S of z would be 1 by 2, which is 0.5. I think it is clearly visible. Yes. Okay, fine. So it is clearly visible, right? So this curve, this nice looking curve, fits exactly between 0 and 1, and that is what we are going to use in logistic regression. So our logistic regression algorithm boils down to what? I think I have space over here, and okay, this is visible as well. So our logistic regression algorithm boils down to h of x 1 by 1 plus e to the power minus g of x, right? This is our sigmoid function, right? 1 by 1 plus e to the power minus z, where z we have is g of x. And what is g of x? Where g of x equals to mx plus c, m into x plus c, which was our regression line, which can be multivariable, which can be single variable, that can be like, that depends particularly on your number of features, right, which are present in our data. Fine. If this is not clear, then it would become clear when we do a hands-on session. Don't worry about that. Or you can even rewind the video and just go through the video twice. But still, when we will be coding this particular whole algorithm, we'll be seeing that. Okay, fine. So now talking about this g of x. So g of x as a function of x, we can say we can just remove this constant, and we can say g of x equals to mx, right? Just neglecting the constant. And to keep them in shape, we will just take m as m transpose, right? So g of x equals to m transpose x. So we have this m transpose x, and I think you must have studied about transpose and all. We won't be going into matrices and properties of matrices, but this, we have m transpose. So where m equals to m1, m2, m3 till your mn, which is kind of and this mn as this mn and mn plus 1, which is our c value, which is the coefficient we just ignored, right? And this x is the number of features you have, so x1, x2 till xn, and for the last value we have 1. So on multiplying, you would get this mx plus c form. When you multiply m transpose with x, you get this sweet little mx plus c form. Fine. So now my prediction function will transform to, okay, so just changing the slide. Okay, so now we have changed the slide, so we have a clear page. So now my prediction function will transform to somewhat like this, which is be h of x equals to 1 upon 1 plus e to the power minus m transpose x. Just replace that g of x over here, right? Plotting this graph. So now let's plot graph of this one, and I think you would have guessed like how this graph would look like. It would be similar to the sigmoid function graph we really look at, and but just the values would be a little bit changed, and our perspective would be a little bit different. So let's see. So this is the graph. Here we have the sigmoid function. Oh man, it's looking pretty nice. 1, 0, and here we have this 0.5 value. So this graph, this is an exponential graph first of all, and this graph moves very fast between 0 and 1, and that is what exponential is all about. Now looking minutely to the graph, what we can observe is, our sigmoid function s of z equals to 1 by 1 plus e to the power minus z. This was a sigmoid function, right? And as we discussed, when we have this s of z, if z is greater than 0, then s of z is greater than 0.5, right? Fine. So using this, our hx, which is s of m transpose x, right? So this is our sigmoid function, this is our prediction function. So you can see s of m transpose x, which would be equal to 1 upon 1 plus e to the power minus m transpose x, and when hx would be greater than 0.5 if this m transpose x is greater than 0. Just taking this analogy, you have this, right? Fine. So this proves that the prediction function we have come up is the sigmoid function. The sigmoid function, this one, is non-linear function, right? Sigmoid function we have is non-linear function, and the decision boundary, this is the decision boundary, m transpose x is a linear decision boundary. So graphically we look at this statement as this is the graph, and this here we have, suppose, some data points. So we have a binary classification graph, and decision boundary goes something like this, right? So we have this x1 here and x2 here. Okay, my bad, it was not visible, now it is visible. So fine. So we have these two classes, and if a data point lands over here, then this would be hx greater than 0.5, and it would do the prediction accordingly. And if the point lies over here, then hx would be less than 0.5, and the prediction would be accordingly. Okay, so logistic regression, we won't, so in logistic regression we won't be using this prediction function, but we need to find a hypothesis function where we have our learning parameters with x similar to what we did in like linear regression. We will be finding coefficients of x1, x2, x3 and so on, and the intercept as well. So in next session we would find how the best fit line comes, and how decision boundary is able to minimize the cost function and all. This was just these two previous sessions were just a basic layering of transition from linear regression classification towards logistic regression classification, why we don't really use linear regression for classification. Yeah, so that's all. We will be diving into logistic regression in the next session. Bye bye. Thank you.